Okay, in section 1.9, we're going to continue our discussion of linear transformations. First, we defined an identity vector last time with our E1 and E2. So remember E1, right, would be 1, 0. E2, these would be the identity vectors in R2, right, where E1 and E2 are in R2. So just refreshing you of that definition there. All right, we're also going to add a definition here for a identity matrix. So the identity matrix includes all of the identity vectors, okay? So we call that capital I2, that's our identity matrix. We could have I4, for example, would include 4 of the identity vectors. So we get the 1 on each line, right? That would give us a pivot in each row and a pivot in each column. So those identity matrices are square, okay? Now, we can have identity vectors that fall short of an identity matrix and get something similar, but it's not actually an identity matrix. So for example, if we had E1 would be in R4, and we had E2 also in R4, so 0, 1, 0, 0, and E3 in R4, so 0, 0, 1, 0. Those three together, the matrix that would be made up of E1, E2, and E3 for my columns, would not be an identity matrix. It wouldn't be I3, but it is very similar to an identity matrix. Okay, just to give you those ideas. Okay. Now, one of the things we talked about last time was using the transformation we have to go with those identity matrices. So if I have T of E1 is equal to 3, 7, 1, you'll notice here I'm going to write this as a row vector or as an ordered triple. Okay, so 3, 7, 1. And I'm going to use equals in quotation marks here because these aren't really equal, but they represent the same thing. 3, 7, 1 written horizontally like that with commas, or the column vector 3, 7, 1. They're practically equal. Okay? They refer to the same thing. So if we write it in this horizontal form, we know that that's going to imply the same idea over here. Okay, so for example, T of E1 is equal to 3 copies of E1, 7 copies of E2, and then 1 copy of E3 would be another way of writing it. Okay, and then let's say I have another vector here that's T of E2. It's equal to 2, 1, 2. Okay, which I could write as 2 copies of E1, 1 copy of E2, and 2 copies of E3. Now, I know my transformation here, T of X, has a matrix A that corresponds to it. Okay, and I can write that matrix A given my information here. I have T of E1 and T of E2. Okay, so my matrix, my first column, 3, 7, 1 from my T of E1, and my second column, 2, 1, 2 from T of E2. So if this is my matrix, okay, that means I have 2 columns, okay, which means that what's being multiplied by here is x1, x2. Okay, so notice there's just 2 in the input, and then I have 3 rows in the output. We'll call that B1, B2, and B3. So my transformation here, T, notice, goes from R2 to R3, okay? So my identity vectors here are E1 and E2, okay? So 1, 0, and 0, 1, okay? So this transformation maps from E1 over to E2. Now we can make some additional observations about this matrix, okay? I can row reduce this matrix, okay? So I take my matrix, and I will show you something here with the calculator while I'm doing this. So I enter a 3 by 2 matrix, okay, so 3 rows and 2 columns. So 3, 2 on the first row, 7, 1 on the second row, 1, 2 on the third row. Okay, and I'll go back here. I go back to the matrix menu, go over to math. We'll come down here to RREF, and I'll do matrix A. And what you'll notice here is it's going to tell me an error for an invalid dimension. Okay, the calculator will not compute an RREF. Even though one exists, the calculator won't compute it because of the way it works. Newer models may, but some of you may be using an older model like this one. You know, it's just at 83, not at 84. Newer models may take care of this bug, but just so you're aware. So what we can do is I can just go in here and make it square. Go ahead and make it 3 by 3. If you have more rows than columns, it won't do an RREF. We just know that it's really 3 by 2 is what we're looking at. So I can work with that, and we know we see 1, 0, and so we can ignore that row, that column of zeros, I should say, because we added that just to get the calculator to work for us. So I get 1, 0, 0, 0, 1, 0. We see that that row reduces, so that means those rows, those columns, I should say, not those rows, those columns are linearly independent. I have a pivot in each column. Also, we notice those two vectors are not multiples of each other, so we could determine it that way as well. So that means that my two vectors, I have two dimensions or two different points of context there. So that means that my equation has no free variables. And if I have no free variables, this is going to be 1-to-1. It's going to be a 1-to-1 transformation or an injective transformation. Remember, those mean the same thing, injective and 1-to-1, which means every input here, x1, x2, that's in R2, goes to exactly one output in R3, and that output is unique amongst all of the inputs, okay? Now, we also know that R3 has a lot more spots in it than R2, so that means it can't cover all of R3. So there are plenty of points in R3 that we cannot get to using these two vectors. Okay, you can find plenty of vectors you could put here that would give you an inconsistent system. Okay, so it is 1-to-1, but it is not onto. Okay, but our big takeaway here is that we can write these equations a few different ways, right? So for example, on this system, I have my x1 vector 371. So this is really x1 times 371 plus x2 times my vector 2, 1, 2. Okay, and when I multiply that out, I would get another vector that would be 3x1 plus 2x2. Second row would be 7x1 plus x2. The third row would be x1 plus 2x2. Okay, and so I can go in between these different notations, right? Here I have a more of a system notation. I could set each of these maybe equal to 0, have a system of equations, as opposed to a vector equation here or a matrix equation here. Okay, so several different choices. So if you have a linear transformation, okay, we're going to look at theorem. It's theorem 10 in your textbook, and I'm just going to put it in front of the camera here just so you can read it. It'll save me a little bit of writing and a little bit of time. Let me focus that just a little bit for you so it's a little bit clearer. Okay, you can see what the situation is there. Okay, so we have our transformation from Rn to Rm. There exists a unique matrix. Okay, so notice this is a unique matrix. Okay, there exists a unique matrix A such that T of x equals Ax for all x in Rn. And in fact, that matrix where the jth column is the vector T of Ej, where Ej is the identity matrix, the column of the identity matrix. Just means it's an identity vector. Okay, so if you need to write that down, you can also take a look at that in your e-text or your physical copy of the textbook if you have one in section 1.9. That is theorem 10 in chapter 1. Okay, so we again see that this A, that's our big thing here. A is the columns is the linear transformation applied to those identity vectors. Okay, that's our big takeaway here. The linear transformation is the columns of the transformation matrix are the transformation applied to the identity vectors. Okay, so if you know what the identity vectors look like, what happens there, then you can determine the matrix. Okay. So let's consider a transformation maybe that we're familiar with from algebra. You know, let's think about a stretching or a dilation transformation. So if I have T of x, remember x here is a vector, is equal to 3x. Again, remember x is a vector. Okay, and we're doing this dilation transformation. Okay, well, I know what E1 is. E1 is 1, 0, and E2 is going to be 0, 1. So we're doing this in R2. Okay, T is going to be a transformation that goes from R2 to R2. Okay, well, I can compute T of E1 very easily. T of E1 is just multiplying by 3, so I get 3, 0. T of E2 then is multiplying by 3, so I get 0, 3. Okay, so I can determine that the matrix then of my transformation, T of x, is equal to Ax, where A is equal to these vectors, 3, 0, and 0, 3. Okay, easy to determine there for something like that, just with a constant multiplying those vectors. Now, maybe we have something that's a reflection or something like that. So let's take a T of x reflects x, and again, remember x is a vector, over the x-axis. Okay, so remember we're still working off these same E1 and E2. Again, we're going to say t goes from R2 to R2. Okay, so it's going to reflect over the x-axis, and it goes from R2 to R2. Okay, again, I have my same identity vectors. So let's think about what the picture of this looks like. Okay, the picture is very valuable here. So I have this vector that's along the x-axis 1, 0, right? So this is my E1 vector. When I reflect it over the x-axis, I'm sitting on the x-axis, so it's not actually going to go anywhere. Okay, but my E2 vector that's going up the y-axis, when it reflects over the x-axis, t of E2 is going to actually be negative E2. Okay, so E1, remember, is going to be 1, 0. E2, though, it's going to turn 0, 1 into 0, negative 1. So that would mean my matrix here, A, would be equal to 1, 0, 0, negative 1. Again, because it's the relationship of the linear transformation to the identity vectors. So if you know what happens to the identity vectors, you can write down the linear transformation. Okay, you can write that transformation matrix. Okay, we actually looked at a couple last time. We looked at a projection onto the y-axis. We looked at a stretching transformation. We looked at reflection transformation with the parallelograms. It was the last thing in the video for 1.8. Okay. Now the other thing we should notice here is that we could do a rotation. Okay. So let's make another transformation here. T rotates x, again, remember x is a vector, about the origin by 45 degrees. Okay, so let's look at what happens here. Again, I have my E1 vector. Okay, this is E1. So when I rotate it 45 degrees, it's now going to shoot out horizontally that way. Okay, so I took that vector and rotated it that way. My E2 vector that points vertically, it's going to now stick out in the second quadrant. So that's T of E2. Okay, and I still actually have a right angle in between them. So this one went over there. Okay, so let's look at what the points were. So E1, remember, is 1, 0. Okay, its new point is going to move 45 degrees. So think about what you know. It's a unit vector. We actually rotated it along the unit circle. Okay, so if I rotate it along the unit circle, I know the x-coordinate is the cosine of 45 degrees, and the y-coordinate is the sine of 45 degrees. Okay, so T of E1 then going to be cosine 45 degrees, sine 45 degrees. And a similar thing is going to happen for T of E2. Okay? Now T of E2 takes that point and rotates it along. Okay, but it started out up here, right? We actually started at the vertical spot. Okay? So T of E2 is going to have that different transformation. I'm going to get negative sine of 45 degrees and cosine of 45 degrees. Okay, so what we see here is 45 degrees is exactly the rotation measure here. Okay, so for any rotation, okay, any rotation by theta, by some angle theta or phi, whatever Greek letter you use for your rotation, your transformation matrix is going to be the cosine of that angle, sine of that angle, and the negative sine of that angle, cosine of that angle. Okay, so that's the elegance there. That works for any angle theta. Okay, any angle theta will work for those rotations. So if you're given a matrix, if you're given an operation, you want to figure out what happens to the identity vectors. And whatever happens to the identity vectors are going to be your columns in your transformation matrix, T of E1 and T of E2. Okay. So next we're going to look at a couple more different ways we can write these style of questions. Okay. So let's say I have T of x1, x2, x3, x4. So I've written out the variables here rather than just calling it the vector x like we normally do, okay? And it tells me that t of x1, x2, x3, x4 maps my vector to x1 plus 2x2. Sorry, I got an extra comma in there. x1 plus 2x2, 0 for the second coordinate. Third coordinate, x3 plus 4x4. Fifth coordinate then is going to be x2 minus x3 plus x4. Okay? We see what our transformation is there. Okay, that's x1 plus 2x2, 0, x3 plus 4x4, and then x2 minus x3 plus x4. Okay, so let's consider what this is. This is a times my vector x1, x2, x3, x4. Okay, writing it as a column vector instead of that horizontal vector. And we know out here it's going to spit out x1 plus 2x2, 0, x3 plus 4x4, and then x2 minus x3 plus x4. Oh, I wrote 4x4, just x4. Okay. So as I look at this matrix then, these are actually the rows of a linear system. Okay. I would be augmenting these rows with this vector. So my matrix A then, I can just read off the rows from it. It's going to be 1, 2, 0, 0. I know it's 4 by 4 because I have 4 outputs and 4 inputs. My second row is going to be all zeros. My third row would be 0, 0, 1, and 4. Notice it's x3 and x4 here. And then 0, 1, negative 1, and 1. Okay? Now, we might be asked if that matrix is, if that transformation, and by extension that matrix, is 1-to-1 or onto. Okay, and so for that, we want to find the reduced row echelon form of it. So I'm going to row reduce that matrix. Okay, so I'm going to put in a 4 by 4 matrix on my calculator. 1, 2, 0, 0, 0, 0, 0, 0, 0, 0, 1, 4 in the third row, and then the fourth row, 0, 1, negative 1, 1. Okay, then we row reduce that matrix. When I row reduce that matrix, I get 1, 0, 0, negative 10, 0, 1, 0, 5, 0, 0, 1, 4. And then all zeros for the bottom row, which isn't surprising because we know an all zero row has to go to the bottom. That also tips us off there has to be a free variable. So notice x4 is free. So if x4 is free, you cannot be 1-to-1 because if you have a free variable, you know that means there are non-trivial solutions. Okay, you could write down what some of those non-trivial solutions are, right? You have that x1 is equal to 10x4. Again, we're moving it to the other side of the equal sign. x2 would be negative 5x4. x3 would be negative 4x4. And x4 is free, so x4 just equals x4. You could also write that in a vector, right? x4 times the vector 10, negative 5, negative 4, and 1. Okay, so we can write that in a vector notation as well. So we have lots of choices there. But if I have a free variable, it is not 1-to-1. Okay? And if I have a free variable, I also don't have a pivot in every row here. Okay? So I don't have a pivot in every column, so that takes out say that again. So if I have a pivot in every row, that's going to make it onto. If I have a pivot in every column, that's going to make it 1-to-1, right? So a pivot in every column is 1-to-1 because if I have a pivot in every column, I don't have free variables. If I have a free variable, I'm not 1-to-1, okay? So let's summarize our conclusions here that we just talked about, okay? So if the system is onto, right? Surjective means it covers all of the codomain. The codomain and the range are the same if it's onto. That means there is a pivot in every row. If it's going to be 1-to-1, that means there is a pivot in every column. Okay? And going hand in hand with the idea of a pivot in every column is that if you have a non-trivial solution, to ax equals 0, then that means you are not 1 to 1, because that means you don't have a pivot in every column. You have a free variable. Okay, so non-trivial solution AX equals 0 means you have a free variable, which means you are not 1 to 1. Okay, so all of these representations are tied together. Okay, we also have those geometric representations, okay, that we talked about just before that. Okay, next we have some written out ways we can ask about these linear transformations. Okay, so let's say I have a transformation T. T maps from R2 over to R2. Okay, and I know that E1 maps to 3E1 minus E2E2. And I know that E2 maps to itself. Okay, so reading this off, this tells me that T of E1 is equal to 3, negative 2. I just read the vector from the expression there. Okay, I know I need 3 copies of the x-coordinate, 2 copies of the y-coordinate. And it tells me that T of E2 is itself E2, which we know is 0, 1. So from that, I can write my matrix A for T of x equals AX. All right, my matrix A for T of x equals AX. Let me zoom out just a little bit there. Got a little too wide for my camera. T of x equals AX. So I can write my matrix A then is 3, negative 2, and 0, 1. Okay. Now let's say we tack something onto this transformation. So that was T. So we're going to have a transformation S that's also going to go from R2 to R2. And it applies the transformation T. Then it reflects over x2 equals negative x1. Okay, so let's think about what x2 equals negative x1 is in terms we're a little more familiar with, what we work with a lot of times, you know, x and y. What this means is y equals negative x, right? That's effectively the same thing. Okay, so let's think about what happens if I just ignore the t part first, right? So I'm going to call this S star to mean that it's just this reflection part. Okay, so just this reflection part is going to represent S star. Okay, it's just a name for a transformation. So if I do S star on E1, okay, let's think about the visual here. So I have my vector E1, okay, it goes out at 1, 0. I'm reflecting over y equals negative x. Okay, I reflect over y equals negative x. So where it's going to send that transformation by doing that is it's going to flip the coordinates and make them both negative. Okay, so I go from 1, 0 down to 0, negative 1. Okay, so it flips the coordinates and makes them both negative. If I take S star of x1, x2, you know, my standard x vector, it's going to give me negative x2 and negative x1. So it makes them both negative and flips their position. So the same thing is going to happen then if I go to S of E1. Well, it's going to take T. Remember, it applies T first, so 3, negative 2. And then when I apply it, it's going to flip. So it's going to be 2 and negative 3. So it flipped the sign of both of them. The 2 became a positive 2. The 3 became a negative 3. And it flipped where they were. So then S of E2 is going to do the same thing. It's going to be negative 1, 0. It makes them both negative, but 0 is neither positive nor negative. So my transformation matrix for B, so we'll say that S of X is equal to a matrix B. We don't want to call it A because we already used that. My matrix B would be 2, negative 3, negative 1, 0. Okay, and so if I wanted to apply this transformation X to another vector, this transformation S to another vector, let's call this vector lowercase b. Lowercase b is 2, negative 1. Well, S of B would be equal to 2, negative 3, negative 1, 0, multiplied by this vector B that I picked out. And so we multiply that in the conventional way, going across the rows and down the columns in the second entry. So 2 times 2 is 4. Negative 1 is 1. So 4 plus 1 is 5. And then negative 3 times 2 is a negative 6 plus 0. So 5, negative 6. Okay, and we also know from solving equations, again, this all fits back together. Chapter 1 is really notorious about everything fitting kind of on top of itself. You get 2, negative 3, negative 1, 0. And if I augment that with 5, negative 6, okay, if I row reduce this system, okay, let's take a look at it here. If I go to matrix, edit, I'm going to go with a 2 by 3 matrix here. This is 2, negative 1, 5, 3, 0, and negative 6. Okay, and I come back here and row reduce that. Oh, got the, yeah, it should be 2, negative 3. Sorry, the shadow of my calculator got me there. Then I typed in the wrong number there, negative 3. There we go. Now I have the same matrix I started with. So now if I do RREF, you see I get that 2, negative 1 that I input there. Okay. So once you know the transformation matrix, you can do all the things you know how to do. So I'm going to get 1, 0, 0, 1 and augment that with the 2, negative 1 then that I started with. Okay, so that all fits together, right? 2, negative 1 is in the domain. 5, negative 6 is in the codomain, which in this case is the range, because notice these are independent columns. Independent columns is going to give us something that is onto, going to give us onto. Okay, since I have a square matrix, I have a pivot in every row and a pivot in every column, so it is 1 to 1 and onto. Remember that the word for 1 to 1 and onto together is bijective. Okay, should remember that from a previous class. Bijective means 1 to 1 and onto. Okay, the bijective is 1 to 1 and onto, which would be the case here for that transformation. So notice we stacked 2 transformations on top of each other. Okay, so since both transformations are linear, any composition of transformations is also linear. Okay, any composition of transformations. So anytime you do one transformation and then another, any composition of transformations is linear. Okay, and that should read linear transformations. Okay. And linear transformations are matrix transformations. So any composition of linear transformations is linear. Any composition of matrix transformations is linear. And if it's linear, then I can write a matrix for it. Okay? So we can stick those matrices together in such a way that it gives us a new matrix. Okay? So we can combine all of those things together to help us complete the problems we need to. Okay? So there's a few different notations, but they ultimately line up to the same things, okay? We do the same processes. We talk about the same ideas in each one, okay? Again, if you have any questions, please get in touch with me. I'd be happy to assist you, office hours, by email, whatever it might be. You know, the earlier the better. You don't want to fall behind as we start to get to some of those first quizzes and checks for understanding. And then the first tests and the like be coming up very soon as well. So please stay on top of things. Please make sure you're making progress. Take a look at the course calendars. Make sure you're getting where you need to. And again, be in touch if you have any questions. Okay, thank you, and I'll see you. We will be starting Chapter 2 coming up in our next section. Again, there is a 1.10 in the textbook, but we will skip over that section. We'll be looking at Chapter 2, which is matrix algebra. Again, a chunk of this will seem very repetitive because a chunk of what we talk about in matrix algebra refers to what we have learned here in Chapter 1 about linear systems, okay? So let me know if you have any questions, and I'll talk to you in Chapter 2.